Hey everybody, welcome to today's lecture for analysis of algorithms. This is lecture 13 and it's on connectivity. The video might be a little strange this week because Windows 11 hates me and so I haven't been able to get video working. But I think it's going to be fun nonetheless. Okay, so as usual, we'll start with something about, well, what is connectivity? Okay, so you know that a graph is connected if there exists a path between every pair of vertices. So basically what that's saying is a graph is connected if I can get from any vertex to any other vertex using only the edges that are in the graph. Okay, that doesn't mean there has to be an edge between every pair of vertices, because I can, go between vertices by going through other vertices. So I could get from vertex 2 to vertex 0 by going through vertex 1, for instance. So looking at this graph, would you say that it's connected? I hope you would, because I can get from every vertex to every other vertex. But if we look at this graph, there's a slight difference here. Is this graph connected? No, not really, because I can't get, for instance, from vertex 0 to vertex 1. Right? Like there's just no way to do that. There's no path to get from there, from vertex 0 to vertex 1. Now, that's all very well, but we're concerned with algorithms. We're concerned with sort of generalized procedures. So how do we test if a graph is connected? Do we have a way of just, figuring out from any graph, is it connected? So previously, we have seen connected graphs. Can you guys remember? Yes, we saw trees. So trees were connected acyclic graphs, right? So if we have a graph, we can tell if it's connected by constructing a depth-first search tree from the original graph, right? Because that's going to attempt to construct a tree from the original graph. And if it manages to, then the graph must be connected, right? Because if this tree, which is a subgraph of the original graph, is connected, then the original graph must also be connected, right? So as an example, let's say we've got this graph over here. Arbitrarily, I might decide to do a depth-first search from vertex 1. Okay, I could try from any vertex, doesn't really matter. So let's say I started from vertex 1. Then my depth-first search tree might go to vertex 4 and then 2, and then it'll hit a dead end, so it'll go back to 4 and then back to 1, and then from 1 it'll go, okay, well, there is another child, so I can go to 0. From 0 I can go to 3, and the depth-first search will then terminate because there's no edges that it hasn't seen before. And when it terminates, I can check, well, have I been to every vertex? And yes, I have. So in this case, that means the graph is connected, right? So I can keep track of this just with like a Boolean array. I can keep a true or false for every vertex. And then as soon as I see a vertex, I can set its visited property to true so that I know I've been there. Then at the end, I can just scan through that array. If all I see are trues, then I've been to all the vertices, and otherwise I haven't. The other graph that we looked at earlier was this one. And let's say, again, I did a depth-first search from vertex 1. Okay, so I'll start from vertex 1, maybe then it gets to vertex 2, and then to 4. And then from 4, it can't go anywhere, so it's going to bubble up back to 2. And from 2, it can't go anywhere, so it's going to go back to vertex 1. And then it terminates because there's nothing else it can do. Then I can look and see, well, did I visit every vertex? And in this case, no, I didn't. So the graph is not connected. Okay, so straightforward. I can just do a depth-first search and figure out whether a graph is connected that way. But that just gives us the sort of binary property. A graph is either connected or it's not connected. Okay, and that's cool for a lot of problems that we need to solve. But sometimes we might care about how connected a graph is. Like, is it really well connected, or is it just sort of precariously connected? So, for instance, if I had like a computer network, and that computer network would get disconnected if one node went down, then that wouldn't be a particularly good computer network, right? I'd want some redundancy maybe. Okay, so although that network is connected, I sort of want it to be more connected. Okay, so we then introduce this idea of n connectedness, where n is some integer. And okay, I have a baby that's awake. I'll be back in a second. Okay, I'm back. I know that felt like just a few seconds, but that was a long time. I've forgotten where I even was. I think I was talking about the notion of n-connectedness. And we can think of n there as the measure of how connected the graph is, right? So you can get like 2 connectedness or 3 connectedness or 4 connectedness. And the higher the number, the better the connection, if that makes sense, the more connected the graph is. So how we define this measure is that a graph is n-connected if removing any n-1 vertices could not disconnect the graph. Okay, so what it means is that the graph would still be connected after the removal of any n-1 vertices. Okay, so when we talk about a graph that's connected, we could also be saying that it's one connected, because what we're saying is that the removal of any 0 vertices still leaves it connected. That's a silly way of putting it, but we could say that something was 2 connected. And when we say something is 2 connected, that would mean that it would still be connected even if we removed any one vertex. Okay, so 2 connected, we have a word for that, is biconnected. Now, why do we care about how connected a graph is? So, I mean, one possibility is like network design. You know, as an example, the internet was designed for use during the Cold War, and the idea was that if you blew up any particular computer, you wouldn't break the internet, right? Like, let's say you were like a foreign government and you're trying to destroy the internet. If you use the strategy of just like blowing up random computers, that wouldn't be a very good strategy because the internet is very connected, right? So just blowing up computers isn't going to do anything. On this idea of connectivity, one piece of research we did a few years ago was related to medical interventions in HIV. So what our research was about was, what's the best policy decision government can make in order to reduce the spread of HIV? So we constructed this sort of virtual society that had various virtual people in it, and these people had sexual relationships, and we modeled the dynamics of these relationships according to the best info that we have. And we were then trying to figure out, well, what's the right thing to do? Do we want to circumcise people, or do we want to push more heavily on condom usage, or more education, or that sort of thing? And where the connectivity comes to play is that most sexual relationships are not particularly important in the spread of HIV. The ones that matter are the connections made by the really promiscuous people. So you've got most people who are just not that promiscuous, right? You have very few sexual partners. And then you've got some people who just have like a ton. And those people are the most important for modeling the spread of HIV. And I mean, I guess this is almost irrelevant, but our study found that circumcising promiscuous men was probably the best way to reduce HIV in terms of the cost versus the effectiveness, which was, a quite interesting result actually. But it couldn't really have been done without an understanding of connectivity and how this can be modeled. Okay, so here's an example of a graph that is connected, right? So that means it's one connected. So is it also 2 connected? Is it also biconnected? Well, looking at it, are there any vertices which if we remove it would disconnect the graph? Like, is there one, any vertex where just removing one vertex would disconnect the graph? Well, yes. So that means it's not bi-connected, right? It's not bi-connected because if I removed vertex 1, for instance, there'd be no way of getting from vertex 4 to vertex 0. So vertex 1 sort of stops the graph from being bi-connected. Similarly, vertex 0 does it as well, because if vertex 0 was removed, I couldn't get from vertex 3 to vertex 1, right? So vertex 1 is known as an articulation point. Okay, that means it's a point, a vertex whose removal causes the graph to become disconnected. Okay, and in order to determine if a graph is bi-connected, we could try to find the articulation points. Because if we don't find any articulation points, we know the graph is bi-connected. Okay, so how could we find the articulation points? Is there any way that you can think of that we could figure out which vertices, when removed, would disconnect the graph? Okay, so the straightforward thing is we could just brute force it, right? We could say, well, I need to know if there are any vertices, or I need to find all the vertices which, if I remove them, will disconnect the graph. Now, I know how to check if a graph is connected. I just do a depth first search, right? So our algorithm could look as simple as the one presented on the slide, which basically says, you know, just one by one, remove the vertices from the graph and see if the graph gets disconnected, right? So that means first I'll remove vertex 0 and I'll check, well, is this graph connected? And if it isn't, then vertex 0 is an articulation point, because I just removed vertex 0 and that made the graph disconnected, right? Then I'll start with the original graph again and I'll go to vertex 1 and I'll remove it and I'll check if the graph is disconnected. And if it is, 1 is an articulation point. Okay, so that's a quite straightforward algorithm. Basically just uses the definition and goes, well, if I want to find an articulation point, I can just remove it from the graph and see if the graph is disconnected. But the thing is, this would take a long time. This would kind of suck, because I mean, we're doing so many DFSs, right? We just, every time we remove a vertex, we then do a DFS. Then we put that vertex back, and then we remove the next vertex and we do a DFS. And then we remove, and then we put that vertex back and we remove the next one and we do a DFS. And it's one of those things, like, I'm getting tired even just saying it, because it's such an unpleasant amount of DFSs to do. And remember, DFSs, I mean, they're reasonably cheap. They cost big O n plus m, where n is the number of vertices in the graph and m is the number of edges. But now we have to do that as many times as there are vertices. So now it takes us big O n times n plus m. Okay, so this whole thing gets pretty expensive. Can we do better? And well, since I'm asking the question, and this is an algorithms course, you know the answer is probably yes. That's an example of a heuristic or an informed guess. We know we can do better, because otherwise I wouldn't be bringing it up, would I? So we do have a better algorithm that can do this. It's called Tarjan's algorithm, and it relies on some properties of trees, right, in order to do this. Because, well, the idea is that we're talking about connectedness, right? And we know that a tree is a sort of minimally connected subgraph of a graph, okay? Because trees are connected, but if you remember from the trees chapter, we said that any edge, removing any edge would disconnect the graph, would disconnect a tree, basically, right? So trees are connected, but very precariously so. There are no cycles or anything like that. Okay, so how Tarjan's algorithm works is that it says, okay, well, you want to find the articulation points in a graph G, right? So what you do is you first make a depth first search tree T from that graph G. Okay, we saw how to do this in the section on depth first search trees. And then, well, remember, T is a subgraph of G that has all the vertices from G. So that means, I mean, it's pretty much the same as G, except that there's extra edges in G that aren't in T, right? T is a subgraph. Now, what we can do is we can think of those edges as like spares, okay? And I'll tell you why we I'm thinking of them as spares next. So now, if we removed a vertex from T would become disconnected, right? Because T is a tree. So like its children would just not be able to get back to the root, right? So like here's an example of a tree. Okay. Now let's say I removed vertex 2. Then there's no way of getting from vertex 4 to vertex 0, right? So the child of 2 becomes disconnected unless the one we removed is a leaf node. But let's say that it's not a leaf node. Then its children get disconnected from the graph, right? So that would mean that 2 is an articulation point, right? But if we're talking about the original graph G, not the tree T, then 2 is only an articulation point if there's no spares that can be used to reconnect the subtree. So let's say in G there was actually the edge node 4. It didn't make it into the tree, but it was in the original graph. Then now when I remove vertex 2, I can sort of replace it with that spare edge 4 node that I didn't use in the tree T. Okay, so how Taugen's algorithm works is by sort of keeping track of these spares and seeing then, well, look, if I remove a vertex, can the children still get connected to the tree just by using a spare? Okay, that's just an intuition, but now we have to think about how to actually do this. Okay, in order to do this, we keep track of some properties of any vertex. Okay, and we keep track of these properties so that we know if they have a spare that's gonna be useful. Okay, so for every vertex we keep track of its DFS number, which is just a count of when that vertex was encountered when we were making the DFS tree. And we keep track of the back number, which is defined as the lowest DFS number of any vertex that can be reached from V without going through its parent. Okay, now if that made no sense, that's okay. I can't even follow it myself. So I think we can follow it better if we take a look at what's happening here, what those numbers mean. Okay, so let's say we've got this graph G. Now what we're going to do is we know we want the DFS number, which is sort of a list of when we encountered each vertex. So let's start doing this thing. Let's start the tree with vertex 0. Now you'll see I've added these little blocks, and these blocks are for keeping track of the DFS number on the left and the back number on the right. Okay, now the DFS number was just a sequence. So since vertex 0 was the first one we encountered, it gets the DFS number 0. Okay, then maybe the DFS goes to vertex 3, which then gets the DFS number 1 because it's the next vertex that was encountered. Now you may be thinking, why am I giving these vertices new numbers? They've already got numbers. Well, the reason is that the numbers on the vertices, when we see them here in the graph, they're meaningless. They have no semantic meaning. They're just numbers. They're just arbitrary numbers. So they don't help us do anything from an algorithm's perspective. What we want is a meaningful number. Now what the DFS number gives us, by keeping track of when the vertex was encountered in the construction of the DFS tree, it's giving us an idea of sort of how close to the root that vertex is, and this will become important later. But for the moment, we've got these DFS numbers. Maybe the next one we encounter is vertex 4, which means that it gets DFS number 2. And from vertex 4, there's nowhere to go, so the algorithm bubbles back to vertex 3. And from vertex 3, there's nowhere else to go, so it bubbles back to vertex 0. And then from vertex 0, it goes, okay, wait, there's another child, so I'll go to vertex 1. But when we were at vertex 4, we will have seen that, you know what, there's also another edge going from 4 to 0. So that's one of our spares. That's a back edge. Okay? So we call these spares back edges in case I didn't mention that earlier. So we've got that back edge 4 0, and so we put it on our graph. When we get to vertex 1, we see that it'll get DFS number 3 because it was encountered next, and then maybe we go to vertex 5, so it gets DFS number 4, and then we go to 2, which gets DFS number 5. Okay, and at 5 we'll notice that there's a back edge from from vertex 2 to vertex 1. So we draw that into our graph, right? So we've got these back edges and we've got our DFS numbers. But what do we do about the back numbers? Well, remember the back number was a measure of how far up the DFS tree we could get from vertex V without going through V's parent. Okay, so as an example, the back number of 5 is a measure of how far up the tree, so how close to vertex naught we can get without going through 1. Okay, and you can sort of think of that as important just because we're trying to figure out if, in this case, if 1 is an articulation point, right? So we're saying, well, can 5 get above it in the tree without going to it, without going through it? Okay, and we'll look at how that's done. So the back number, we said now, is a measure of how far up the DFS tree we can get from a vertex V without going through V's parent. Now let's think about where we can get to. From any vertex V, we can get to the vertex itself, right? Because we're already there. So that's the most low effort destination we could have, is just stay where you are. Then from any vertex, we can get to its children without going through our parent, right? Like if we were at 5, we can get to 2 without going through 1, right? Because that's just sort of, we can go down the tree. Okay, and that means we can get to anywhere that the children can get as well. Okay, so we can get to V's children, and we can get to anywhere that V's children can get. The other thing we can do, if we're at a vertex, is we can go up along the back edge that it has, right? So that means we can get to V itself, we can get to V's children and to anywhere the children can get, and we can go along back edges to wherever the edge goes. Okay, so the back number then becomes the minimum of the DFS number of V, because we can get to the vertex itself, the back numbers of V's children, because we can get to wherever the children can get to, and the DFS numbers of the destinations of the back edges leading from V, because we can walk along the back edges. Okay? Now let's look at how this plays out. When we're trying to figure out the back number of 0, for instance, what is the back number of 0? Well, it's the minimum of the DFS number of 0, which is 0, the back numbers of V's children, which we don't know, and the DFS numbers of the destinations of the back edges leading from V. It doesn't have any back edges, so that's fine. So that means it's the minimum of 0 and some unknown numbers. And we can't possibly find that minimum, right? So that means we can't actually find any back numbers until we get to the leaf nodes, because those don't have any children, so we can figure out their back numbers. So in this case, when the DFS gets to vertex 4, we can say, well, what is its back number? Its back number is the minimum of its own DFS number, which is 2. The back numbers of its children, and it doesn't have any children, and the DFS numbers of the destinations of any back edges going from it. Now in this case, there's a back edge going to vertex 0, which has DFS number 0. So that means the back number of vertex 4 is the minimum of 2 and 0. So it's 0. Okay, so that's why we filled in a 0 here. Then the DFS will bubble up and it'll say, okay, well, for vertex 3, what is its back number? Well, it's the minimum of its own DFS number, which is 1. The back numbers of its children, it's got one child whose back number is 0. And the DFS numbers of any destinations of any back edges. It doesn't have any back edges. So that means it's the minimum of 1 and 0. So that makes its back number 0. Okay. The root has a DFS number of 0. And its back number is the minimum of its own DFS number, the back numbers of its children, and the DFS numbers of destinations of back edges. Now here there's a bit of a shortcut, because this thing's DFS number is 0, and there's no way that number is ever going to be less than 0. We know that the minimum is going to be 0, so we can just fill in a 0. It doesn't even matter. We know the minimum of because the DFS number of V itself is 0, we know the back number is going to be 0 no matter what the other quantities are. Okay, and then we'll look at vertex 1. for vertex 1, the DFS number is the minimum of, the back number is the minimum of its own DFS number, which is 3. The back numbers of the children, which is unknown, and the DFS numbers of the destinations of back edges, and it doesn't have any. But so that means we can't know it because we don't need to know the back number of the child, and the same applies to 5 until we get to vertex 2. For vertex 2, the back number is the minimum of its own DFS number, which is 5. The back numbers of its children, and it doesn't have any. And the DFS numbers of the destinations of its back edges, and it's got one back edge which goes to the vertex with DFS number 3. So that means what we get is the minimum of 5 and 3, which gives us 3. Okay. For vertex 5, its back number is the minimum of its own DFS number, which is 4. The back numbers of its children, it's got one child which has the back number 3. And the DFS numbers of the destinations of its back edges, and it doesn't have any back edges. So that means it's the minimum of 4 and 3, which gives us 3. And for vertex 1, we go through the same process. Its back number is the minimum of its own DFS number, which is 3. The back numbers of its children, it's got one child whose back number is 3. And the DFS numbers of the destinations of its back edges, and there are no back edges, so its back number is 3. Okay, so now we filled in all the back numbers. And that's fine, but what do we do with these back numbers? Well, here's the cool thing. If there's a vertex that has a child with no connections to vertices above V, then V is an articulation point, right? And that kind of makes sense because remember, when we remove the vertex V, as we said earlier, all of its children are going to get disconnected from the main graph, right? Now, if there's no connections from that subtree back up to items above it in the tree, then V must have been an articulation point, right? So as an example here, if we removed 5, 2 would get disconnected, right? So if there was no way of jumping back up using a spare or a back edge, then it would mean 5 is an articulation point, right? In this case, it isn't an articulation point because I could just go along the back edge of 2. 2 is connected to 1, so it doesn't, it's not an articulation point. But if that back edge wasn't there, then it would be, right? But what that means is that this measure of how far back up the tree I can go is all I need to determine if something is an articulation point. What I can say is that if any child of V has a back number that is greater than or equal to V's own DFS number, then V is an articulation point. This applies to all vertices which are not the root vertex. The root vertex is a special case which we'll talk about later. But looking at this, if I look at, say, vertex 3, does it have a child whose back number is greater than or equal to 3's own DFS number? Well, 3's DFS number is 1. Its child's back number is 0, which is not greater than or equal to 1. So that means 3 is not an articulation point. Okay. If I look at vertex 4, can any child of 4 have a back number that's greater than or equal to V's own DFS number? Well, no, because it doesn't have any children. So that one's not even worth thinking about. But let's look at vertex 1 then. So vertex 1, because remember we're looking at non-root vertices, so I'm not going to look at vertex 0. But vertex 1, let's look at whether it is an articulation point. So what we need to see is, does it have any children whose back numbers are greater than or equal to its own DFS number? Now, its own DFS number is 3. Does it have any children whose back numbers are greater than or equal to 3? Yes, it does, because 5's back number is 3, which is greater than or equal to 3. More specifically, it's equal to 3, but, that's by the condition. That means 1 satisfies our condition, so 1 is an articulation point. When we look at 5, does it have any children whose back numbers are greater than or equal to its own DFS number? Well, its own DFS number is 4, and its child's back number is 3, so that 3 is not greater than or equal to 4, so 5 is not an articulation point. When we get to 2, is 2 an articulation point? Well, it doesn't have any children, so it can't be an articulation point, right? because we said it's only an articulation point if it has a child whose back number is greater than or equal to its own DFS number. Now, it doesn't have any children at all, so, you know. Okay, now, the special case we talked about earlier is the root. The root is an articulation point if it has more than one child. So that's a pretty straightforward thing. In this case, is the root an articulation point? Yes, it has two children. So that means 0 is also an articulation point. So we end up with two articulation points in this graph, 0 and 1. Why is the root an articulation point if it has more than one child? Well, if we removed vertex 0, its children wouldn't be able to reach each other, right? And I can guarantee there are no edges that would have connected these two subtrees, because if there were, the DFS would have gone completely differently. Like, let's say there was an edge between 5 and 3, and that edge would mean that 0 is not an articulation point. Well, then when I was doing the DFS, I would have gone from 0 to 3 to 4, and then I'd have bubbled up to 3, and then I'd have gone down to 5 because that edge would exist, right? So the thing is, the only way for the root to have more than one child is if these two subtrees have no connections between them. Okay, and if they have no connections between them besides the root itself, then the root must be an articulation point, right? Because the graph would be disconnected if it wasn't there. Okay, and that's the entire algorithm. Now, the cool thing about it is that, in this case, I separated finding the DFS number from finding the back number just because I thought it was easier to explain that way. But in the actual algorithm, the DFS numbers and back numbers are calculated in one pass. So as I do the depth first search, I'm calculating the DFS numbers and the back numbers at the same time. And so it just takes one pass through the thing. So it's big O n plus m, right? All that's happening is I'm doing a bit of extra work in order to store and calculate and store the DFS numbers and back numbers, but it's a constant amount of work. Per edge. So it stays at big O n plus m. Okay. So that was a sort of high-level intuitive overview of how Tajin's algorithm works, and I think it's quite a clever algorithm. So it's actually really fun to take a look at the book to read the algorithm and code, and also to read the proof that the algorithm works. It's actually quite a cool proof. So I'd encourage you to check it out. Okay, so I hope that lecture on articulation points was fun. It's actually, I found it quite fun to do. So I hope you enjoyed it. Thank you everybody for listening.